Hello, I'm Sue Nelson and welcome to the Planet Earth podcast with the sound of a tail-shaking rattlesnake. That's because I'm in the venom unit of the Liverpool School of Tropical Medicine, and it has the largest collection of venomous snakes in the UK. Also in today's podcast, if you didn't know much about the European shag, you soon will.
Shags are kind of completely black and kind of more delicate black seabirds. And you can't really see it at the moment because it's getting on to winter, but in the summer they have that kind of flicked back crest hairstyle. Absolutely marks them out as a shag.
Almost 2 million people around the world are bitten by snakes each year. Yet, despite having effective treatments in the form of anti-venom, more than 95,000 of them will die from their bites. And this is why I'm in the Alistair Reid Venom Research Unit here in Liverpool. I'm with Dr. Nicholas Casewell and the unit's head, Dr. Robert Harrison. We're all wearing safety glasses, not least because, after recording that rattle of a rattlesnake, Rob is about to put my microphone at the end of a pole so that we can hear the distinctive puff of a puff adder.
I'm just going to open the cage. The snake just bit the microphone. But you can see how very, very alarming that sound is, particularly if you're walking at night on a footpath without a torch.
Oh, that was terrifying. Oh! That sounds like somebody heavy breathing, doesn't it?
Other people have said it sounds elementally evil and think of Darth Vader.
Oh, well, it certainly gave me a terrible shock. Nicholas, you have around 200 snakes in your collection. We're in one of the smaller rooms of your venom research unit. Some quite vivid green. I don't think I've ever seen a snake that green before. It almost looks like the sort of green highlighter colour.
We've got some mambas here, which are the green ones you referred to, incredibly quick and agile snakes. And we've also got some spitting cobras, a number of different varieties. And you can probably see...
Just behind me here?
Yeah, behind you. One of them just coming out.
It's got that very sort of saucer-shaped wide neck.
That's right, yeah. We call that a hood, and that's a threat display that it's giving us right now.
Well, that's because I went a bit too
Absolutely,
close to the glass,
yeah.
isn't
So
it?
he's giving you a warning there, and if you're lucky, you might actually shoot some venom. You can see venom actually on the inside of the glass where he spat out you before. They aim for your eyes, so that's another defensive mechanism they have. They try and shoot venom into your eyes to basically tell you that he's dangerous and to stay away.
It's incredibly hot in here. I can feel the sweat starting to pour down the side of my face. How hot is it in here?
About 30 degrees, so...
Oh, that explains it.
Yeah, we try and maintain all the rooms at the best temperature for all the snakes, so we have to suffer a little bit for them. Here's a banded spitting cobra we've got from Africa. He's keeping our eyes on us, and... But you'll notice that despite all this movement and us being very, very close to them, they're not actually trying to bite us. And that's quite important because everyone thinks that snakes are quite aggressive and that will bite you at any opportunity. But really, they just want you to leave them alone. You know, they want to feel safe and protected.
You sound very affectionate towards your snakes here. But what damage can they do with their bites?
Well, they can be incredibly dangerous. And the venoms that they have are incredibly potent. They've got a really complex mix of different proteins that when they're injected into your bloodstream can really do horrible damage to your body. So you can have effects such as bleeding, you can bleed from your eyes and from your gums, you can have what we call tissue necrosis where your tissue actually dies. So you'll often see that when people are bitten on their feet or on their hands, the tissue kind of eventually turns black, and this can often lead to amputations. And then the snakes we're actually with here, the mambas for example, these are what we call neurotoxic snakes. When they inject their venom, they stop the prey moving, that's how they're able to eat them. And they do this by injecting their venom, which actually stops the animals from breathing, so they get paralysed. And then once they're paralysed, they can be kind of eaten at will.
Rob, you're the head of the unit here. Are the snakes representative from one area in particular?
We primarily have a focus on the snakes here from Africa because we're trying to do something about the snakebite problem in Africa. And what we're trying to do there is take the venom from these snakes and then send those to antivenom manufacturers who will then make antivenom from that venom. And it's that antivenom that is actually crucial now in Africa because it's responding to a crisis in supply of this life-saving therapy at the moment.
How serious a problem is snakebite in Africa?
It's very serious. It's been estimated that at least 32,000 people die every year from snakebite. And also there's been something like 8,000 to 9,000 amputations as a result of snakebite. In some areas of Africa, particularly the rural savanna areas, it's not unusual to have hospitals where 7 out of 10 patients are snakebite victims.
So these snakes have been collected out in the field and brought here to Liverpool?
They have. We've got snakes from West Africa, particularly the spitting cobras, the saw-scale vipers and the puff adders from Nigeria. And that's because Nigeria suffers possibly the highest mortality rates from snakebite in Africa. And at the moment, there's not an effective treatment. And so the Ministry of Health came to us asking us to see if we could help with their problem. And we involved the University of Oxford and Professor Worrell in this attempt. And we've got the snakes here, we're extracting venom from those snakes. That venom is then sent to antivenom manufacturers in Wales and another one in Costa Rica who are making the antivenom. That antivenom has now been tested by us at a preclinical level and then tested by Professor Worrell and our Nigerian colleagues in human patients, in possibly the largest clinical trial of antivenoms ever conducted. And that trial indicated that 2 of these antivenoms were very safe, very effective, and because of the nature of their manufacturing system, cheaper than anything else that was on the market. And since the last 5 years, we've delivered 32,000 vials of this life-saving therapy to Nigeria, which equates to about 16,000 life-saving treatments.
Nick, how are the antivenom antidotes made?
The antivenoms are made by injecting very small subtoxic amounts of venom into animals, which generates an immune response. And that doesn't hurt the animal, but it means that we can collect things which we call antibodies, which are immune proteins that are specific against the venoms. So what this means when you actually inject an antivenom into a person is that these antibodies, as we call them, they find the venom proteins, the toxins of the venom that cause so much damage, and they stick to them and they prevent them causing harm to the person who's been bitten.
Do these have to be very specific to each snake? So would the antivenom for, say, one of this bright green mamba behind me not necessarily be effective if I was bitten by the spitting cobra, the black-necked spitting cobra in front of me?
That's right, yeah. It's very important that the antivenom that you use is specific to the species of snake that was used to make the antivenom. And this is really the problem that we have with antivenom production, that we haven't been able to produce, say, an antivenom that works against every species. There are some antivenoms which are made where you use the venom of multiple species to make the antivenom.
Sort of one bite fixes all, cures all.
Kind of, that's right. But the problem is then that the antivenom is specific to 3 venoms, say, for example. And this is a problem because it means that whichever snake you're bitten by, the antibodies are only specific to 1/3 of that. And that means that you need 3 times the dose of your antivenom, which of course is far more expensive for people, particularly poor people. It also brings in some potential safety issues as well, because large amounts of antivenoms can cause problems in people.
So how do you improve the antivenoms that are available then?
Well, one thing that we're looking at doing here in Liverpool is trying to improve the use of an antivenom against more than just the species that it was used to make that antivenom. And we've been looking at saw-scale vipers, which are quite small African snakes. Up to 80% of all the deaths in Africa are by saw-scale vipers. So what we've looked at doing is, in the laboratory, we've been looking at testing the antivenom that exists against West African saw-scale viper venom. And we've been trying to see whether this would also work against other saw-scale vipers from, say, North Africa and East Africa. And we were really surprised and delighted to find out that it did work in the laboratory. We've been able to show that we can prevent lethal effects of this venom with the antivenom used for West Africa. And that's really important because it means that we can look at expanding the kind of use of the antivenom from one small geographic region to a much larger region. And that's good for patients, perhaps, if antivenom doesn't exist in those areas. And it's also important for the antivenom manufacturers because it increases the demand for their product. And that means that they can reduce the cost to poor people.
Are there other applications, Rob, that come from your research into snakes here?
Yes, there are. For instance, a drug called Captopril, which is used to treat hypertension, has been administered to 16 million people in UK alone to treat their high blood pressure. This drug had its origin in a snakebite from South America, which was known to cause a catastrophic loss in blood pressure. So people exploited that to develop this new drug. And it's an area of research that's blooming around the world, trying to use the very powerful nature of these venom proteins for good.
Robert Harrison and Nicholas Casewell, thank you both very much indeed. This is the Planet Earth podcast, and you can see pictures of some of the snakes here in Liverpool on our Planet Earth online Facebook page. From snakes to birds now. The European shag is a dark seabird similar to a cormorant, but, as its name suggests, can be mostly found along the Atlantic coast of Europe. 1 in 4 of the world's population of European shags can be found in the UK, but over the last 20 years their numbers here have been declining. Hannah Grist, who studies the birds, is trying to find out how the population varies over the winter, and when not observing them on the Isle of May, she can be found at the University of Aberdeen. So I joined Hannah by the harbour, where she was set up paparazzi style with a long lens and tripod.
Well, at the moment we're in a place called Girdleness in Aberdeen Harbour, and we are looking over at the harbour walls in search of European shags.
You've set yourself up with a camera on a tripod with the harbour wall in the distance, so we can see a small sort of lighthouse there. What have you trained your eyepiece upon?
So it's quite a serious scope, actually. So you can use it for viewing things, and you can attach like a camera to the top and take photos.
So this isn't even a camera. This is
just a lens, basically.
Gosh, yeah.
So what you can see in the distance are basically small black seabirds, and they're a mixture of shags and cormorants.
Okay, let me have a quick look down the eyepiece. Oh yes, they've got very long necks and long beaks. Which are the cormorants and which are the shags?
Shags are kind of completely black and kind of more delicate black seabirds. And you can't really see it at the moment because it's getting onto winter, but in the summer they have that kind of flicked back crest hairstyle. Absolutely marks them out as a shag.
You study shags on the Isle of May. Mm-hmm. Isle of May is probably better known for its puffins. So why have you eschewed the sort of cute and cuddly puffin with its colourful beak for sort of a plain Jane by comparison, really?
That's the kind of thing that a lot of people say, and the problem we have on the Isle of May is that everyone comes to see the puffins, they're cute and colourful. But a lot of research has been done on puffins, and a lot less has been done on something like European shag because people see it everywhere and don't think it's a really fascinating seabird. But actually we've learnt a lot using the European shag system. On the Isle of May, we've been looking at them for about 30, 40 years now, so we've got a lot of data behind us that we can use to answer a lot of questions.
And what questions are you particularly posing?
Because a lot of the work we've done on the Isle of May has been during the breeding season, which is when they're there breeding, obviously. But what we don't really know is what's happening to them over the winter period. I mean, this is half the year for birds, so it's ridiculous that we're not really paying attention to what's going on over this time.
Is that because they disappear or because they stay there and keep out of sight?
Well, for European shags, for the Isle of May population, what we think they're doing is that a proportion of the population is staying on the Isle of May over the winter, and the rest of them are travelling up and down the coast, up to 200, 300, 400 kilometres away from the Isle of May and staying the winter in different locations. And what we're really trying to do is find out why they're making that journey and what kind of effect it has on them.
How do you do that then? Do you ring them?
Yes, all the shags on the Isle of May are actually colour ringed. They have plastic rings on the legs that have a 3-letter code in them and are brightly coloured. And this is basically what we're looking for using the telescope, is that we can read the code from a distance, we don't have to recapture them. It means that over the winter we can try and find them and see where individuals are and then relate that back to what we see on the island.
I know this research project is ongoing, but what have you found so far? Any surprises?
I think the surprises are just the sheer distances that some of these birds are going. And also we're kind of looking at if there's any kind of segregation within the population. So if, for example, partners might be moving together or offspring are moving together. And we're not really sure if that's happening at the moment yet, but we have had some anecdotes of partners being seen courting in different locations and juveniles from a single nest having stayed together. So these are kind of interesting things that we could be looking at in the future.
Do populations of European shags tend to stay stable?
Shags are actually quite an interesting seabird because they seem to follow this is what we call a boom and bust dynamic. They breed quite fast for a long-lived bird, but they also can have really high mortality rates. So over the winter in particular, we can lose huge numbers of the populations in what are called winter wrecks. And in around 93, 94, we actually lost about 90% of the Isle of May population in a really bad winter.
That does make it odd then that why only some of the birds leave, particularly when you can get very harsh winters.
The winters are harsh all the way along the east coast, and we don't see so much of a kind of boom and bust effect on the west coast. We think because there are more inlets on the west coast and they can be more sheltered. So shags are really interesting in that for a seabird, and they're diving seabirds, they go for fish, they're actually not waterproof.
A bird that isn't waterproof?
I know, it's one of those things that sounds like a really terrible idea, but in fact they dive really deeply. For birds that just go from the surface and dive down, they can get to about 40 metres. And the thought is that this kind of lack of waterproofing enables them to dive deeper. But what it does mean is that they're very restricted to be able to come back to land to roost because they need to be able to dry out their feathers. And on this kind of unsheltered eastern shores, we think if we're having bad winters, what's happening is they just can't dry out sufficiently and that they might be losing them through hypothermia or really high kind of costs of trying to keep themselves warm.
What use will this information be, apart from the fact that you might be able to apply it to other populations of European shags in Wales and Cornwall and other areas where it's quite rocky and cliffy where they like to be?
Because it's such a long data set we've got on this population and we know the individuals, we're in quite a unique position to be able to look at things like something we called a carryover effect, the effect that perhaps staying in a particular location has on the breeding success in a future season, and that's not something many people have been able to look at. But also from a shag perspective, if we know kind of key locations where they're more protected, where they're surviving better over the winter, that's something that perhaps in the future we might be able to protect for them. So from a conservation perspective, it could have applied relevance.
Hannah Grist from the University of Aberdeen. And if you live in Scotland, you could help Hannah out with her research, as between now and March, European shags are spreading out along the Scottish coast. So if you see one, and binoculars in hand, you're able to identify the colouring on the bird's leg with its 3-letter code, then do let her know by emailing shags@ceh.ac.uk. Well, as you can probably hear from the echo in this room, I've removed myself from all proximity to snakes into the preparation room of the Venom Unit to be with Tamara Jones from Planet Earth Online, who's got some news from the natural world. And in fact, you couldn't get more natural than the Galapagos Islands, which is the subject of your first story.
That's right. Well, researchers from the Zoological Society of London, University of Leeds and the New York State Department for Health have discovered that some of the wildlife on the islands could be at risk from West Nile virus.
What is it?
Well, it's a virus that affects mainly birds, but it also affects mammals and reptiles, and of course, because it affects mammals, that includes us.
How does it spread?
By mosquitoes in exactly the same way as malaria. So if a mosquito got to the islands and it had West Nile virus, there's a risk that it could infect the population of amazing creatures there on the islands.
Have mosquitoes been shown to reach the Galapagos Islands before?
The mosquitoes that spread the virus are actually on the islands already, and they got there in the 1980s, and they probably got there by travelling on aeroplanes just by accident.
Tourism.
Exactly, completely by accident. The problem is that the virus is actually being found in a couple of countries in South America. So the risk is if a mosquito with the virus got to the Galapagos Islands, that could mean that West Nile virus gets to the Galapagos.
Obviously, the threat has been highlighted by the research. Is anything going to be done about it? Are the authorities in the Galapagos going to increase their biosecurity?
That's the aim. I mean, the researchers will probably be in discussion with some of the authorities in the Galapagos Islands, and the most important thing is to enforce biosecurity. So the aeroplanes, military aeroplanes, tourist aeroplanes should be sprayed with insecticides so that you get rid of these mosquitoes so they don't get there in the first place.
Moving on now to what I believe has been an extremely popular story on the website.
Researchers have found that there's a clear link between the solar cycle, the 11-year solar cycle, and the winter weather in the Northern Hemisphere. So what this suggests is that the cool winters we've had in the UK over the last couple of years are linked to the solar cycle. So we've just come out of a solar minimum, and they're saying that that is why we've had such cool winters. What they also found was that at the maximum of that 11-year cycle, we're more likely to experience milder winters in the UK and the rest of the Northern Hemisphere.
Do they know why?
There are fewer ultraviolet rays when there's a solar minimum, and those ultraviolet rays are more likely to generate easterly winds, which bring cool weather from the continent to Northern Europe, and so driving away the milder prevailing winds that would come up from the Atlantic, and therefore bringing cold winters.
Tamara Jones, thank you very much indeed. And that's it from the Alistair Reid Venom Research Unit at the Liverpool School of Tropical Medicine. Do check out our Facebook page. This has been the Planet Earth podcast for the Natural Environment Research Council. I'm Sue Nelson. Thanks for listening.